So I guess most of you already know me, but I'll introduce myself. I am Llorenç Escolà, and I'm doing a PhD here at QuSoft. And today I'm going to talk about quantum position verification, and I'm going to talk about recent results that are done by QuSoft, in particular with some people that are present in this room now, Florian Spielman over there, Philip and René, and someone else that is Andreas Blum, that is in Grenoble. But without further ado, I'm going to start with position verification, which is the main topic that I'm going to talk about today. And like, it's pretty much intuitive. So you want to verify someone's location. Here there's a map, and you want to say, okay, that person or that thing in general is in that location. And that's what I'm going to talk. So there's something that is called position-based cryptography that you can believe me that it's going to be about verifying, well, about using position to do cryptography. If I can just put the watch, because it's falling off. Okay. And I'm going to particularly talk about what I said before, which is position verification. And here there's a party P that wants to commit a set of verifiers. So here they are going to be V0 to Vk, that person P, she's in a certain position, right? So the verifiers are going to challenge that person, and the person is going to send some answers. And we're going to say, okay, that person is here, or that person is not here. So I'm going to give an example. So this is the moon, and actually man went to the moon like longer than 50 years ago now. And you actually want to verify if people went to the moon at some point or not, and it's not fake like that. Because some people still claim that man didn't go to the moon, but whatever. So I'm just going to give a bit of like examples of applications. I don't know, maybe if you can trust someone's location, you are in a call and you can verify that the person that you are talking to is in a bank, like in a certain location of the bank, you're probably going to trust that person more. Or I don't know, it can also be used by the police. I don't know, we are in that position. I see that there's a bombing here. Do you trust? Okay, just verify the position. Or in general, any building can come from the government. Also military things, which is like a bit more ethical. We can think of it later on. But maybe self-driven cars. You can see here, if you want to verify that the car is going on track, if it's self-driven and I don't know, no one else is hacking it. So that could be a future application of it. I mean, we're still far, but it might be an application. So to make it more precise, I assume that this is a prover and it's just going to be me. So assume that I go to Paris and I go for work-related things. But the thing is that there's in Amsterdam my promoter, Paula, that doesn't really trust me. So I wonder why. And then there's also Florian present in this room that didn't and also doesn't trust that I go to Paris for work. And they both think that I go to somewhere else for vacation. And there's a third party in Stuttgart. And for whatever reason, this man, I don't know him, but he doesn't trust me either. So the thing is that they're going to challenge me. They're going to send me a challenge and I have to respond back. So if you think of like the position, you might think of the timing constraints that might take to send the challenge in that position and send it back. And actually, if you just do this, sending messages at the speed of light, so there's going to be a single point of intersection. Like you see, this would be the light on in 3 dimensions, and you have this circle. This is like the reason that you can achieve sending messages at the speed of light. So they are going to coordinate so that they arrive all at the same time. And this is all based on the fact that this comes from Star Wars. But this is actually not physically possible, right? I mean, as far as we know, there's nothing that can go faster than the speed of light. So we are going to base our analysis on that you send messages at the speed of light. They are going to arrive at a certain point, and only at this point, the challenge can be performed. I mean, we'll see that this is not exactly true because you can always break protocols, but this is the main idea. Very well. So saying the example before, I'm going to say that, okay, I'm actually working and they want to verify that I'm in a certain location at the office or giving a talk like here right now. And instead of like enjoying the good weather that we currently have and having a mojito in a parasol close to the beach, which could be likely if the weather keeps going on like that, but very well. I'm gonna make the analysis slightly easier, and we're gonna try to work on protocols to verify the location in a straight line instead of in a plane, like I showed you before in a map, because map can be seen sort of as a plane if you just take Euclidean metrics and stuff. So the thing is that this is going to be the time arrow, and you see the light cone of one of the verifiers. It's going to be that one, and the light cone of the other verifier is going to be the one on the right. And you can see, as I promised before, that this intersects at a point, and they're going to time the questions so that they arrive at this point where I am supposed to be. Very well. So now they send me questions, X and Y, and at time 1/2, I have to perform a challenge, which is going to be computing a function, let's say. And then I have to respond back to them. Very well. If it arrives on time and both answers are correct, they accept my location as correct. But I mean, it's not that easy. Otherwise, I wouldn't be talking about that, I guess. So there's always buts. Let's say that I have two friends, and they're going to be, I don't know, maybe Garazi. But now your name is going to be Alice. I'm sorry. And someone else with a mustache, Pujit, is going to be Bob. Hello, Bob. So the thing is that you are going to cover me. And instead of being me in that position, both parties are going to send the questions. So Alice is going to intercept one of the questions, make a copy and broadcast it. And Bob is going to do exactly the same. So here, their locations, they can both have the classical information. They can perform the challenge F, and they can send the answers back without being at the location. And with that, they can fool the verifiers because the verifiers are going to receive the correct answer at the correct time. So they are going to check mark. Okay, that is a very easy way, because this is a trivial protocol. You just need to be located left and right to the prover that's supposed to be there, and then copy the classical information and send it. Okay, but can we do that in quantum? There's the non-cloning theorem. If you take Dolly, very well-known machine, you cannot copy an unknown quantum state. And as a curiosity, Dolly was cloned the same year that I was born. I don't want to say anything about that, but very well. So what if instead of sending classical messages, you send, there's a question in the chat? Oh, I actually saw it in a talk of his, and then I just took the idea. Good, Chris. So the thing is that what if instead of sending X and Y, you send something quantum, also from one side, and quantum from the other one? And I just put it Q to denote quantum. And then instead of performing a challenge, you do some operation with all the information that you got. And then you have to respond something that can be either classical or quantum. And here, the thing is that these two things cannot be copied. Can you remove this thing? I believe it's not that important, but this type, yeah. This thing cannot be copied in another type. So to make it like more clear, I'm going to give an example, which we denote the people that work in quantum position verification as the quantum position verification BB84. And the thing is that this is mostly based on the idea of QKD, that you send BB84 state and then you measure in the basis, right? So as promised, well,
Another slide, I think, with your laptop.
like the slides again?
Or you click on the slides with your laptop.
No?
Yeah,
They
no.
won't work. Okay, what happens?
Oh, it's just, oh, yeah, yes, the Zoom has.
Okay. Oh, I'm going to start the talk again. Blah, 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 everything. Speed of light, QPV, Lycon, answers, correct, attack, pulling the verifiers, no cloning theorem, quantum position verification. Example. Good, very well. So as promised, you send BB84 states, either 0, 1, plus, or minus. So you send them to the prover, and from the other side, you send a classical bit that is going to denote the basis that you have to measure this qubit. 0 denotes the computational basis, and 1 denotes the Hadamard basis, right? So the thing is that you take the qubit, you measure in the basis, and then you just broadcast the outcome. Okay, that's like, looks a bit like QKD, but here with the timing constraints and stuff. The thing is that this protocol has a con that it can be broken with a single EPR pair that is pressured by the attackers. I'm gonna tell you later on how, but we'll solve it later on, so don't worry about that. And the thing is that, okay, what if we restrict the attackers a little bit? What if we don't allow them to share entanglement? What is the best thing that they can do? So at the end, the protocol can be attacked with at most 85% probability, and you repeat it many times, and you can distinguish like attackers from a honest party, right? Okay, and actually, I'm gonna show, well, it is a big no-go theorem that all quantum position verification protocols can be attacked, which is like bad news in some sense. But on the positive side, the amount of entanglement that they are required to have, like to share at the beginning, it's like, can be really, really large. The best upper bound known so far requires exponential amount of entanglement, which like for practical purposes, it can be really difficult. So the goal, since we know that all quantum position verification protocols can be attacked, is gonna make quantum position verification protocols that are easy to implement, but extremely difficult to attack. And to make it more like a down-to-earth example, if you want to prevent people from drinking Coca-Cola, for instance, you put a can to €1,000,000, right? Who's gonna buy it? So it is something relatively easy, but if you put like high constraints, I mean, it's like reasonable to think that if Coca-Cola is going to cost like $1 million or euro, people are not going to drink Coca-Cola anymore.
So the constraint here is the shared amount of entanglement?
Yeah. Very well. But we also have some experimental implementations. For instance, photon loss. So when you send photons in optical fibers, because that's how you do, because you know in free space there's even more loss, but in optical fibers, like most of them are lost. Let's say 99% of the photons are lost. And that might be a problem. I'm going to show more explicitly how. Measurement errors is also, but this is not that much of a big problem because most of the protocols are shown to be quite resistant to photon to measurement errors, and also slow quantum information. And that's another problem, because if we base everything to sending messages at the speed of light, and we don't have speed of light with photons, can consider the problem. Like to make it more precise, if you have in mind the protocol that I explained, that I showed to you before, you have here on the left-hand side, the problem of photon loss, more graphically represented. And on the right-hand side, the problem of sending information slower than the speed of light. Here we would have the light con, so speed of light. And here, I mean, it's like slower than the speed of light. And here, this is one of my favorite plots, which is the Bermuda Triangle, which encodes like the three major problems of quantum position verification, which instead of Bermuda, we have photon loss. Instead of Puerto Rico, we have slow quantum information. And instead of Florida, we have entanglement by the attackers. The two of the right are the verifiers and provers fault. So it's like due to implementation. And this one is the power of the attackers. Very well. So the thing is that there are protocols that are fully resistant to photon loss. There are protocols that are very resistant to entanglement. And there are protocols that are resistant with slow quantum information. And also you can have this combination. But here there's a problem that we cannot access to this region, which actually we need to implement it efficiently. And the thing is that if you send planes there, boom, they're gonna blow up. And that's what I'm going to talk about, this Bermuda Triangle. So try to keep it in mind. Very well. So for the BB84 case, and here I just denote eta because we're gonna have like eta is gonna be the transmission rate. So I'm gonna consider loss. We have the following problems: the photon loss that I showed you before, the slow quantum information, and entangled attackers that here, I mean, even if you implement it perfectly, it can be perfectly broken. And I'm going to show one by one a bit why this is a problem. So take the advantage of photon loss, first of all. So assume that you have Alice and Bob as usual on those positions. Then Alice intercepts the qubit, makes a guess, so X tilde, and it's either 0 or 1, so measured in this basis and obtains an outcome. The thing is that she broadcasts the outcome and Bob just broadcasts the basis. If the guess was right, so you're going to know that your answer is right. Otherwise, you just claim that the photon was lost. So this thing, if you have something that is below 1/2 of transmission rate, you're going to be correct 1/2 of the time. So you can always say, when you are correct, you respond. And when you are not correct, you just pretend that the photon was lost. So with that, using photon loss, you can perfectly break a protocol. that's what this is sort of a big thing. Any questions so far?
Is there any way that do the attackers also have photon loss?
No, the thing is that we are assuming that attackers do not have photon loss, that attackers don't have errors. We assume the maximum things to the attackers because it's sort of reasonable at some point to assume that they can have maybe some hidden technology that is better than ours, right? Than the publicly known. I don't know if there's a word when you are just working your own thing, then it's like you don't want to make it public, right? So we always assume that the attackers are better than us, assuming that we are as the honest parties. Very well. Taking advantage of slow quantum information. So now I'm going to exaggerate a bit the plot, but assume that the quantum information is arriving slow enough that one party, Alice, can just intercept the qubit and send it to Bob. Bob measures in the correct basis, just broadcast the outcome. And that's it. So you can also perfectly attack it if you take advantage of slow quantum information. Very well. Isn't it known what the probability of photon loss is? Well, depends. Okay, so the photon loss can be really high. At some point I mentioned that 99% of the photons can be lost, but it also depends on the distance. The farther you have to send the photon, the more photon loss there's going to be. And you want to say something, Philip?
It's like 90% per kilometer or something.
90% per kilometer.
Yeah.
And also as a clarification, it's clear that so to the honest party, the photon has to travel all the way, but an attacker could actually try to position themselves as close as they want to the sender. So the attacker might, even with the same equipment, the attacker might actually have lower photon loss than.
Yeah, that's true. You can just position yourself closer, and you intercept everything that person sends. Okay, and taking advantage of entanglement, which was the third problem that we were facing. So here Alice and Bob pre-share an EPR pair and intercept the qubit. And this, if you have that, it's kind of, okay, you think maybe you can just teleport it. So that's what Alice does. So that's a teleportation measurement. So gets classical outcome C, the teleportation corrections. And then Bob, what does is measuring his local register P in basis X and sending the outcomes. And since these two things commute, you can recover the correct answer A, and you can perfectly break the protocol. Very well. And now let's analyze the loss. And that's work that we did with Florian. Very well. So assume here that now we have a certain transmission rate eta. And then we have that the message that is being sent can be lost, this one in here. Very well. So we have to allow an extra answer to the prover. That is also something that has to be valid when you actually perform the protocol, which is this perpendicular symbol, which is going to denote photon loss. And we also introduce some experimental errors that can come either from the measurement device or the channel. You just send a 0, but it flips, so it can be some error at some point. And this is going to be denoted by PERR, probability of error. So actually, if you think it a bit carefully, the probability that at the end the prover responds something correct is going to be eta, because eta times he's going to receive, or she is going to receive the photon, and then 1 minus the probability of being wrong. The probability of saying no photon is going to be 1 minus the transmission rate eta. The probability of being wrong is eta times. Once you receive the photon, you're going to be wrong. And abort is when you send inconsistent answers, because with classical information and with the current technology, you are never going to send some answers that are different to the verifiers. So then you can just put it very strictly that here you abort, or you can put some epsilon. Doesn't really matter at the end, but we can be very strict with that because that is achievable with the current technology. Sure.
When you have the correctness probability, you seem to assume that two different events are independent, so that you can multiply their probabilities.
Yeah, we're assuming that for the honest party, that the error and the transmission rate data are independent.
But you could imagine that photons are sort of more likely to be lost if they are in a certain state, and less likely to be lost if they are in some other state.
Oh.
And then let's say the other events, be dependent on this photon was sent initially.
Yeah, that's actually true. I don't know about that, like in terms of experimental things and how difficult it is, because you're just sending BB84 states. And I don't know if there are some that have more probability to have an error or not, because here it's just sending 0, 1, plus and minus. So it should be like sort of the easiest ensemble that you can send, but probably we have to talk to some experimentalists and ask, do you know anything about that?
So yeah, I think it's a very good point. So I think if you would use the polarization basis and you use polarizations in the plane and not like the circular one, I think then it's pretty uniform. But you're completely right that even to have circular polarization, you actually use a slightly different component, I think, and that might have slightly higher loss. And of course, if you use some other properties like some, I don't know, time bin things or other things, it's a very good point. Then it might actually be different.
Yeah.
But if you think about polarization in the plane, like then I think it's a decent assumption.
Yeah, but even if it is not, at the end, this is in the control of the honest parties that perform the protocol. So the verifiers know it all, so they can just readjust it, and then we can just work with the new probability just adjusted in here. At the end, they know what they expect given the experimental setup. For here, I just assume that. But at the end, I'm just going to show that some attackers want to mimic this, right? But even if it's not independent, they know it, and as long as they know it, it should be okay. But yeah, that's a good point. Thank you for that. And at the end, we're just going to have this probability vector, which is something that the honest party will do, right? And now I'm just going to talk about attacks. So the goal is to mimic what the honest party does, so that you can fool the verifiers very well. So here I'm going to start. At some point, I don't know if you noticed, but I put Q as a qubit and psi as a ket. And the thing is that I'm just going to change it now, because for the security analysis, we are going to do something that is very common, which is purify a protocol. And you think of this as an entangled version, where instead of sending one of those qubits, you just take one EPR pair, that this happens to be the same as this expression. So you send 1/2 of it. And the thing is that this is equivalent to sending a BB84 state, because you can always delay the choice. Like you send half of an EPR pair, and then you measure the other half later on. So, I mean, for the security analysis, you can consider that you send a maximally mixed state. Very well. And here, Alice and Bob, we can argue easily that the most general thing that they can do is Alice intercepts the qubit Q if they don't pre-share entanglement, because this is the analysis if they do not pre-share entanglement, because now I'm going to do the analysis for that, including photon loss, which was not done before. So just once you entangle the qubit with your local resistors, you send a part to Bob and you keep another part. So here, undulated lines are going to denote quantum information, and straight lines classical information. And without loss of generality, anything that Bob could do quantum, since they are separated and they don't pre-share entanglement, I mean, it's going to be done by Alice, and Bob is just going to broadcast the income that he intercepts. And at this stage, they share a state that has no restrictions on the dimensions whatsoever, but the only restriction is like the previous one, that they don't pre-share entanglement. So you have a tripartite state between the verifiers that just kept the other half of the EPR pair, Alice and Bob. And if they have to answer, what is the more general thing that they can do to a state is a POVM, right? So Alice does a POVM depending on the classical information X and outputs answer A. Bob does the same. So, and at the end, they have to respond either 0, 1, or photon loss. And the same for Bob, and they respond, okay? So, and at the end with this, we're gonna have some probability of being correct, some probability of saying photon loss, some probability of being wrong, and some probability of abortion. Very well. And here comes the first result, that we could just find what is the optimal probability for every transmission rate eta, which is given by, well, I mean, from 1/2 to 1, but for less than 1/2, you know that you can always attack the protocol, because you can just do this guessing attack. And at the end, we have that the maximum probability to be correct by the attackers is given by this expression, which is, I think it's beautiful. And now I'm going to give you a sketch of the proof. Any questions so far? So they can drink water.
Is it like an upper bound or an upper
No, this is
bound?
actually tight. So I'm just going to show that how to find an upper bound and then a lower bound, and they match.
This is specifically for the BBH.
Yeah, this is specifically for this protocol. Very well. Proof sketch. So consider these two things that are going to be the projection in the zero if you get input 0, and the projection in here it's going to be the projection in the get 0 if x is 0, and the projection in the plus if x is 1, and similarly here with the 0 and the minus state, where h is the Hadamard transformation. So then the probability of being correct is going to be given by, so those are the POVMs that I described before. This is the state that they present, and this is what the verifier does, which is projecting. So that's the probability of being correct if you answer the same thing, Alice and Bob, that the verifier gets. The probability of being wrong is exactly the same, but if you answer differently from what the verifier gets, both. The probability of saying no photon is at the end the sum of all the no photon things in here, and the probability of aborting is like anything that you send inconsistent answers, right? So actually, we would like to optimize and to see what is the best that you can do being correct, right? And we didn't know how to do that in because this is a maximization problem at the end, and you have to take the supremum over all the strategies, over all the POVMs. But there's one party that does something fixed. And as a matter of fact, now we have a new result also with Florian that we know how to do it, but by then we didn't know. So we did something else to prove it. And the thing is that if you notice, if you sum the two first probabilities, and you denote it by probability of answering with like the probability of being correct plus the probability of being wrong, you get that thing. I mean, this is like the get version of this, but I like it better for the plots, well, for the slides. And this actually doesn't depend on what the verifier does. And we can work it out a bit more, because this looks a bit like a setup for a non-local game. And you have that the quantum correlations like that can be upper bounded by the NPA hierarchy. But the thing is that if you just impose that they have to just send the same answer, this is a trivial bound. I mean, this can be upper bounded by a semi-definite program subject to some linear constraints. But it leads to trivial bound because you can always answer the same thing. And of course, they're going to be the same. I mean, you can pre-agree answering 0. The thing is that now we have to sort of use what we have, because here it's like, if we just upper bound this is very trivial. But we use first that this is a linear constraint also, that inconsistent answers are forbidden. So you put that. Moreover, and here it comes the tricky part, we managed to find some relation between the entries that we have here, which are going to be at the end some entries of a matrix, with what the verifiers do, and the probability of error that you allow in the protocol. And this is, well, those are linear constraints for x and x prime and the inputs. So now, if we go to the previous SDP and we add these two things, we can find an upper bound, what you were asking first, Leo. And as a matter of fact, if you take the convex combination of the strategy that consists of guessing the basis, and then if you are right, you answer. If you are wrong, you don't answer. And the optimal attack that I showed at some point that had probability, well, I didn't show, but I said that had probability 0.85 to win, that provides a lower bound. And they coincide. So they are equal, and that concludes the proof, because we have a lower bound and upper bound that they match. So we find the optimal value. Any questions so far?
So wait, this value is it like for PNs only, or for?
This, you find the probability of answer. So it is, then you can just divide over it and stuff, and you can recover the previous thing. But that gives you how much you can answer, given that that you are not inconsistent, and that you have at most this error. And at the end, if I show a plot, probably it becomes more clear. So if you are in here, this relation between the transmission rate and the error, you're safe. I mean, here, those are different levels of the hierarchy that we impose. And that's to show that actually with the first level, we don't attain the optimal bound, but with some intermediate level, we do. And this line, like the continuous one, corresponds to the attack that we have as a lower bound. So if you are in this region, and those things are things that you know, the probability of error and the transmission rate, you are safe. And if you are in here, I mean, it can be attacked. And that's one of the first results. Very well. One round is secure, but in one round, what does it mean to? It's not conclusive, right? Because if you get a wrong answer, what do you do? If you get a photon loss answer, is that correct or not? If you get the correct answer, is it like enough? And the thing is that here comes the question: can the verifiers distinguish between just repeating the probability that the honest party would do versus something like sequential that attackers can do in our rounds? Like this could be an adaptive strategy, like gambling. I don't know, you go to the casino, you bet in the roulette, and you say, okay, I'm going to bet the color black. And if I fail, I'm going to double my bet to the red or something like that. So we actually have to show that the casino always wins, right? And in this case, we are the casino, so we are going to win. And the thing is that we can implement the payoff function every time that we get a correct answer. And when I say we, I mean as verifiers, we are going to give this number of points. Every time that we get a no photon answer, we are just going to make some penalty. And every time that is in an incorrect answer, we are going to be very severe with that, and we are going to impose quite high penalty, right? So if after air rounds you sum this, a honest party will have expected value positive, but any party that doesn't pre-share entanglement will have a negative expected value. And even more, the thing is that the probability that you can mimic this decays exponentially in R, which is also good news. Okay, so now we show that we can catch some attackers if they don't pre-share entanglement. Very well. But this is still insecure if they pre-share a single EPR pair, and that's like not really good news. But let's analyze this. And this we're going to have sort of for free, that slow quantum information is not a problem. And this is a work also with Llorenç. So we have the BB84 protocol as before, 1 qubit basis and sending the answers. But what if now, instead of sending a qubit and a basis, you send classical information from both sides? You say a bit string of length n and a bit of string of length n also on the other side. And then the basis that you have to measure in is given by a certain Boolean function that says, okay, given the 2-bit strings that you got, compute the function and then measure either in the computational or Hadamard basis. And this, it is shown that, because the thing is that you can just send a lot of classical information, and it's much easier than sending qubits, because you don't face with errors. Well, you do face with errors and stuff, but much less. And now it's sort of known how to solve it, but there's no loss, and it's much easier to manipulate classical information. I don't think I have to convince you about that. The thing is that you can just send bit strings of length n, and with that, the attackers need to pre-share an amount of entanglement that is at least linear with n, which is, you can just make the effort of the attackers much harder just by increasing the size of the bit strings that you send. And also, these people here, which is like Florian among them, showed that this is secure, even though this qubit that you send is arbitrarily slow coming from here. And this is also important, arbitrarily slow, not only because photons in optical fibers are sent at the speed of light, or travel at the speed of 2/3 of the speed of light, sorry, much slower than the speed of light, but also because you are not going to have optical fibers that are in a straight line with long distances. You also want to have a network of optical fibers, and it does not necessarily be a straight line. Very well. And now we are just gonna adapt this and introduce photon laws, and want to still see if this remains secure or not. And the answer is yes, it does. The thing is that, just very quickly, I'm gonna sketch a bit how we proved it, but we managed to show that if there are two states that the attackers use, let's say psi 0 and psi 1 that are good to break the protocol, good means that in some sense they can do better in input 0 and better in input 1 respectively, if that makes sense. Otherwise I can just stop a bit more on that. Then they are distant a bit. So the trace distance is lower bounded by something, which actually means that in some sense, they have to pre-agree for which basis they attack, either 0 or 1, before they communicate. So that restricts attackers a bit. And actually with a counting argument with epsilon nets, we can find one of the main results that we got with Florian, which is the following. So recall that X and Y are bit strings of length n. And here we have that if the number of qubits that the attackers pre-share is linear in n, plus Q, the qubit that is n is arbitrarily slow, and there is photon loss, the protocol still remains secure, which means that we have a region, like that I showed before, with some parameters that the attackers cannot have access to. And at the end, this shows that the probability of being correct, given that you share entanglement, is less or equal at a certain bound, which is a bit ugly, but okay. And the most important thing is that this is a non-trivial bound. And as long as you can show that, you can also show with a similar argument as before, with a payoff function, that you can catch attackers with exponentially high probability after R sequential repetitions. Any questions so far? Very well. What does it mean? It means that now we can push one of the edges of the Bermuda Triangle, and we can send some planes in here. It's nice. Are we done with that? No, we are not, because we are still left with a big region in here. And there's one way to make this nicer, which is, so far we've been using that. You send states that are BBA24 states, 0, 1, plus or minus. And that is resistant to transmission rate eta greater or equal than a half. But what if instead of that, you just add the third dimension that we're scared of, and we add the I and minus I state? I don't know, I had to put some notation. There's no good convention for this state. I don't know if we fear it that much that we don't have a standard notation for this, but this is going to be denoted by the eigenvalues of the Y, Pauli matrix. So what if instead of that, you send 3 bases now, and you have to answer 0, 1, or 2. Then this becomes resistant to photon loss greater or equal than a third. And also this has the intuition of that now here you are going to be right guessing the basis with the probability 1/3 if you do like the same attack as before. I mean, that's a way to show the lower bound. The upper bound comes from another place, but it's less intuitive. And the thing is that, surprisingly, the more bases you put, the more, if you just put more bases in which you can measure a qubit, the more resistant it becomes. Here, if we have n bases, this will become roughly tolerant for eta greater or equal than the number of bases that you have to measure the qubit in. And this is good news, because we can do the same analysis for that thing, and at the end, we can push a bit more this Bermuda Triangle, and we can have planes flying over there. But I'm sorry, there's always a but. You have, and we have actually, some region here that's still not currently achievable, like having that as a true thing. So let's fix this, right? And here, Florian, Philip, Rene, and Andreas is where they come. How to fix this? Oh, very well. So now I'm going to talk about something more general than the protocol that I was talking about. And so let's consider that we have a general protocol P, that has arbitrarily slow quantum information and classical answers. This is going to look like this. So if you look, you can send quantum messages from any site, and those can be arbitrarily slow, and classical information from every site. The thing is that you have to do some operation here, but the constraint is that you have to answer something classical and something classical, right? And as usual, undulated lines are representing quantum information and straight lines are representing classical information. Okay, so this is going to have a transmission rate eta V coming from the verifiers. So how can we fix loss in such a setting? So we can think of the following. So we call it, given a protocol P, we define its committing version, which is the following. And here I just slash this, because at the end, the result is that we can just forget about this photon loss, which is very nice because it constituted a big problem. And as Philip said before, it was like 90% of the photons are lost in 1 kilometer, right? Which is like very big thing. So assume that we have this protocol. So the previous protocol, now we modify it. So first you send the quantum information, and when it arrives, you just do photon presence detection, which is something that it can be done experimentally, and experimentalists are quite optimistic with that. I mean, it's already being done, but you just say, okay, I got the quantum information and I will play this round. So after you keep it, and after, and also when you keep this photon, it can be a bit of loss, which is a loss that only comes from the prover. But this loss is going to be in a time delta, which can be really, really small. And now, after this time delta, you get the classical information coming from both sides. And then you do the challenge that you have to do. And then you answer. Is it clear? This thing is like exactly the same, but you receive slightly before the quantum information in a time delta. And then after the time delta, you get the classical information and you use it to perform the challenge that you are supposed to. And then you answer. And as I said before, here I'm going to show the main result that we have. That is that basically you can get rid of this loss in here. So just to summarize a bit, this is a protocol, and this is its committing version. That you just commit that you are going to play when you receive the photon. And here comes the main theorem, that we say that every quantum position verification protocol P with arbitrarily slow quantum information and classical answers becomes loss tolerant on its committing version PC. More precisely, we have that the probability to attack the protocol when we are facing these two photon losses, which are the ones in here that are the total photon loss, this is less or equal than if you have the original protocol, but only with the loss that happens in here, not all the loss that we originally had, plus some things that I'm defining now that are in the control of the verifiers, which is an epsilon if we allow them to commit different, which would be also something inconsistent, but we say, okay, let's put some epsilon probability that we get different outcomes as committing, plus C, if we don't want to be really strict and we say, okay, since we are not going to send all the possible pairs X and Y, that would be like quite a lot of effort. We don't require that the committing from the attackers or from the verifier is correct in all of the pairs, but just in a fraction. And those things, if you are very strict, you can send them to 0. So actually you just recover the same probability, but if you just relax a bit, you have pretty much the same. At the end, you have that the probability to attack does get rid of this loss. That is like the big loss that we are facing. And yeah, well, that's the explanation, but with the arrows and stuff, I should have used it because it's nicer instead of only the pointer. And I think that I'm slightly earlier on time. The consequence is that photon loss is no longer a problem. I mean, that's a bit optimistic because with the protocols that we have, we can face smaller photon loss ranges, which are the ones that I told you before. and they can tolerate little photon loss from the prover. And I think that with that, I am just showing that the Bermuda Triangle no longer becomes a problem and we can send planes over it all. And with that, I would like to thank you for your attention.